screening test for a disease shows a positive result in 90% of all cases where the disease is actually present. So that's the probability of a positive test given the disease is 97%. Sorry, 90%. And it also shows a positive test in 7% of all cases where it's not present. So the probability of a positive test given not having the disease is 0.07. Yeah. If a result is positive, the test is repeated, assuming the second test is independent of the first test. If the prevalence of the disease is 1 in 250, so the probability of having the disease is 1 in 250, which is 0.004. And an individual tests positive twice, what's the probability that the individual has the disease? So we want to find the probability of having the disease given 2 positive tests. The thing about this is it feels hard, but it's actually really almost exactly the same process as finding the probability of having the disease given 1 test. So I'm going to make a tree because I find that to be the easiest way to do this. And I know that if I want to find this, it's going to be equal to the probability of having the disease and having 2 positive tests divided by the total probability of having 2 positive tests. Somebody, I don't remember who, asked me about total probability in this reflection. Whenever you're doing this conditional probability and you use this version of the formula, which I think is the one I always do, where it's the probability of this and this divided by the probability of this bottom part, you're almost always using the formula for total probability. You're trying to find the total, and there's no other words to use. You're trying to find the total probability that you have 2 positive tests. So let's make a tree diagram. So first, we can either have the disease or not. And the probability of having the disease is 0.004. And the probability of not having the disease is 0.996. Okay. And then from there, normally from there, we'd say, okay, what's the probability of having a positive test or not having a positive test? And it'd be, a branch with a 0.90 and then another branch we didn't care about with a 0.10. But now we actually want to know what's the probability of having 2 positive tests given that you have the disease. Well, the tests are independent. So given that you have the disease, the probability of the first test is positive is 90%. And then when you do another test, the probability that test is positive is also 90%. Because the tests are independent. So the probability of having 2 positive tests, given that you have the disease, is 0.90 squared. And the probability of other things are we don't care. Although it would be 1 minus that. Same deal here. You either have the probability of having 2 positive tests, given that you don't have the disease. So, right, you have the first positive test, there's a 7% chance of having that, or a 0.07% chance of having it. And then you do another test because you had a positive test, and there's another 7% chance of having that positive test. So it's a very, very small chance of having 2 positive tests given that you don't have the disease, right? It's 0.07 squared, which is like 0.0049 or something like that, or 00, I forget how many zeros it is. Anyway, so then we just follow the paths. So I want the probability of having the disease and 2 positive tests. That's the probability of having the disease times the probability of having 2 positive tests given that you have the disease. I will also point out, notice that when you want to find the probability of having something and something else, it's the probability of the first thing times the probability of the second thing, because when you want something and something else, you multiply the probabilities together. So it's the probability of having the disease times the probability of 2 tests given that you have the disease. And then in the denominator, we want all the ways you can have 2 positive tests. So it's this path to having the disease and 2 positive tests, 0.004 times 0.90 squared. Or more generally, whenever you use base formula, because this is base formula just done with a tree, the thing that's in the numerator also always ends up in the denominator. Plus the other way of having two positive tests, which is not having the disease and having two positive tests given you didn't have the disease, which is going to be 0.996 times 0.07 squared. I don't actually care to calculate this. We could calculate it, but that's not really the point. The point is this is how you would do the problem. And then you could use a calculator to get whatever the value is. And it should be a pretty, excuse me, it should be a relatively high value compared to what it would be if it was the problem of having the disease given one positive test. So the two positive test situation isn't really that much worse. It just feels hard because it's less familiar, but really it's the same tree that we would have done with one positive test, just we're having two positive tests and you're squaring the probability of one positive test to get the probability of two positive tests. That's kind of it. Questions about this? All right, let's look at these other couple questions that were not hard once you know how to do them, but just not easy from the get-go. So where'd you go? Yeah. Okay. So here's homework 8, problem 3. You roll 2 fair dice. Find the probability that the first die is a 4, given the minimum of the two numbers is a 3. So I don't want to list out all 36 ways you could roll 2 dice, although we could. So, right, you have the first die and the second die, and the first die can be a 1, 2, 3, 4, 5, or 6. And the second die can be a 1, 2, 3, 4, 5, or 6. But I really just want to list out the ways we get what we want, or we get what our reduced sample space is. So you roll 2 fair dice. We want to find the probability that the first die is a 4, given, I want to know what the given space is, given that the minimum of the two numbers is a 3. So first off, I can't have anything in here, right? I can't have a 1 or a 2. In fact, I can't have anything in here, right? If either die is a 1 or a 2, then the minimum won't be 3. And similarly, you can't have anything in here, right? I don't want any of this. I don't want any of this. I don't want any of this. It looks like this is my sample space where you have 3, 3, 3, 4, 3, 5, 3, 6, or sorry, this is my reduced sample space where you have 4, 3, 4, 4, 4, 5, 4, 6, or you have 5, 3, 5, 4, 5, 5, 6, or you have 6, 3, 6, 4, 6, 5, 6, 6. That looks like my reduced sample space. So I want to know what the probability. So let's say that, right, this is the first die. So what's the probability that I suppose the labeling I've done is maybe not the best for that to be the first die. Let's say this is the first die and this is the second die. So I want to know, I roll 2 fair dice. What's the probability that the first die is a 4, given the minimum of the two numbers is a 3? Well, ooh, I've actually gone a little too big here, right? So I actually don't want all this even. If you pick 4, 4, the minimum isn't 3, or any of these here. So actually, we don't want any of these results either. For the minimum of the 2 dice to be a 3, one of the 2 dice has to be a 3, and the other die has to be bigger. So these are the only 1, 2, 3, 4, 5, 6, 7 ways of getting a minimum of a 3. There's only one of those ways where the first die is a 4. So the probability that the first die is 4, given that the minimum is 3, is 1 way out of the 7 ways in my reduced sample space. Yeah. So another way you could do this, which is harder, is to do it as, right, the probability of this and this divided by the probability of this, which is kind of the same work, But the probability of this and this, okay, the first die is a 4 and the minimum is a 3. Well, that's the only way of having that. So the probability of that is 1 out of 36 divided by the probability that the minimum is a 3. Well, the probability that the minimum is a 3, there are 7 out of 36 total ways that can happen. You're really kind of doing the same work, it just feels less nice. So instead of doing it this way, which is still equal to 1/7, I would do it that way. Okay. Got one more. Definitely a number of people asking about this question in office hours. It still seems worth looking at. And the question was, and I'm going to actually change the question a little bit to make it a little bit more challenging. I want to find what's the probability of, so let me back up just a tiny bit. Let's say we flip 7 coins. What's the probability of getting no more than, let's go, fine, we'll go 6. No more than 6 heads given at least 2 heads were flipped. Okay, so again, we're trying to find a conditional probability. We're trying to find the probability that the number of heads is, so let's see, we want no more than 6 heads. So 6 should be the biggest number of heads. So the number of heads should be less than or equal to 6. But it feels like, right, not the most straightforward language. Right? No more than 6 heads, you're kind of no more than 6. Okay. More than 6 would be 7, but I want no more than 6. So I don't want 7. I want less than or equal to 6. But you kind of, sometimes you just have to talk it out with yourself. Like, what does that mean? Given, I feel like they use different words here too, but I don't remember what they were. I wonder if I can find that problem. Not that one, not that one. Sorry, one sec. Curious. Yeah. Find the problem. No more than 6 heads given. No, at least 1. I'm doing at least 2 though. Okay. Okay. So no, the number of heads of those equals 6, given that the number of heads is greater than or equal to 2. And so what we want to do is we want to do a reduced sample space kind of deal. And this is where things, so this is where things are a little bit tricky. So I want to know how many ways, well, actually what I really want to start with is I flipped 7 coins. How many ways, how many different results are there? Well, each coin has 2 possibilities, heads or tails. So you can have heads or tails and heads or tails and heads or tails and heads or tails 7 times. The number of ways you can flip 7 coins is 2 to the 7th power. Now, the tricky part about this is that you're like, well, James, if I flip the first coin is a head, the second coin is a head, right? Is that the same? And the answer is kind of no. We're kind of thinking as each coin is being distinct. So you can imagine like the coins are numbered or different colors, right? So like if you flip the first coin as a heads and the rest are tails, that's counted as different than flipping the second coin as a heads and the rest are tails. Okay. So there are 2 to the 7th, which is equal to, I think, 128 ways you can flip 7 coins. Now I want to know what's the probability of getting less than or equal to 6 heads, given that there were at least 2 heads. So I need to think about what the given reduced sample space is first. So when you flip 7 coins, you can either get 0 heads or 1 head or 2 heads or 3 heads or 4 heads, 4 heads, or 5 heads, 5 heads, not heads, or 6 heads or 7 heads. Okay. So let me ask you guys, if you flip 7 coins, how many ways are there of getting 0 heads? Exactly. There's 1, which is equal to 7 choose 0 ways of getting 0 heads. all of them are tails, and there's only one way all the coins can be tails. But if I want to know how many ways there are of getting one head, well, now there's more than one way of getting one head. The first can be a head and the rest are tails. The second can be a head and the rest are tails. The third can be a head and the rest are tails. So there are 7 choose 1, which is equal to 7 ways that you can get one head. And we could go on, but we don't need to. So there are 7 choose 2 ways of getting 2 heads, there's 7 choose 3 ways of getting 3 heads, and so on and so on and so on. But I want to know about my given sample space, my reduced sample space. So this stuff here, this is my reduced sample space. How many things are in my reduced sample space? Well, there were 128 things in the total sample space, but there's 8 things that aren't in there, right? There's 8 ways of flipping 7 coins where you don't get at least 2 heads. So this reduced sample space has 120 different events, elements. I don't know. Yeah. Events is probably not the right word there. There's 120 entries. Or there are 120 different ways you can flip 7 coins and get at least 2 heads. Great. Now, I want to know, given that we're in this space, so there's 120 things to choose from, what's the probability that one of these things happens? Well, how many ways are there that one of these things happens? Well, instead of adding all those up, I'd rather figure out what that is and subtract it off. How many ways are there of flipping 7 heads? Oh, I see Ethan has already answered the question because it's the same answer as the one before. The number of ways of getting 7 heads is the same as the number of ways of getting 7 tails. One way. 7 choose 7 if you like. But 7 choose 7 is the same as 7 choose 0. So out of these 120 ways of flipping 7 coins and getting at least 2 heads, only one of them has more than 6 heads. So the other 119 of them have less than or equal to 6 heads. So the probability of this is going to equal 119 ways of getting what we want in our reduced sample space divided by 120 ways of things in your reduced sample space. So 119 out of 120 would be the answer to this question. Excuse me. I do think it's worthwhile to approach these conditional probability questions. So I should say the ones that are kind of like, not like the disease ones where you're given the probabilities. When you're able to like to count the number of things in your sample space or reduced sample space, I do think it is usually conceptually easier to think about, okay, how much stuff is in my reduced given sample space? Divide that in your denominator, and your numerator should be how many ways you can get what you want in that reduced sample space. I do think that's a better approach than trying to do something else. Okay. Excuse me. So those were the examples I wanted to go over from the last homework. Let's go ahead and take a quick look at the final review problems here. I feel like of all the things, let me see. Yeah, so we could look at linear differential equations, but I feel like linear differential equations, we might as well look at nonlinear, because linear and nonlinear, I mean, they both get the same stuff, but the nonlinear ones are harder typically. So, sure. Yeah. Let's look at an example of a nonlinear differential equation. Let's kind of just do all the things, because yes, I know your final exam is going to have a number of things on it. Certainly nonlinear is going to be on there. And I think that's kind of something that encompasses a lot of stuff. So let me just grab a problem. That one's too easy. Let's look at that one. Sure. This is problem 9 from section 10.4 in case you're curious. So we have, I'm going to write it slightly differently. With the following nonlinear differential equations. I know I said I was going to grab something from the review, but I feel like I'll leave the review problems for you guys. So dx dt is equal to x minus 6y squared plus xy. Is that right? Yeah, that's right. And dy dt is equal to 8x plus 4xy. Okay. Double check. Yep, looks good. So we want to do. Oh, you know what? That's because it's not available yet, Zin. Oh, sorry, not to call you out. Yeah, so the final review solutions are not available yet. Let me double check. I can make them available though. They'll be available at midnight tonight, but I can change that. Let me change it to today. Just so you guys. So again, I do encourage everybody to attempt each problem without looking at the solutions, and really, you're going to have to take a final. You're not going to have solutions, right? So definitely try your best to look at to do the problems without looking at the solutions. But the solutions should be available now. Please do let me know if they are not. Well, let's go ahead and look at this, and we're going to do all the things. We're going to find the equilibria. We're going to find the Jacobian. We're going to find the null lines. We're going to do every dang thing we can with this. So eigenvalues, eigenvectors, yeah. Maybe not eigenvectors, because that's not really a thing we do for the. Okay, well, we probably should do a linear one after we do this. So let's go ahead and find the equilibrium. So we're going to set each of these equal to 0. And to me, it looks like this one might be easier to deal with. So I'm going to factor out a 4x actually. Factoring out a 4x, I'm left with a 2 plus y. So I'm getting x equal to 0 or y equal to -2. And I can definitely plug those into my original, to the other one to find the equilibrium. Unfortunately, there's no real factoring to do here. So if I would also have the intent of graphing the null lines, I should try and solve for x or y as a function of the other variable. And here specifically, it looks like it's easier to isolate x. So if I was going to think about graphing the null line, setting this equal to 0, I would leave the x's on the left. So x plus xy equal to positive 6y squared. Factor out an x. So x times 1 plus y equals 6y squared. So x equals 6y squared over 1 plus y. So these are my null lines. This is my x null line. These are my y null lines. Let's go ahead and find the equilibrium. So if x is 0, to plug in 0 for x here, or maybe even 0 for x here, y is also going to have to be 0. So x equal to 0 is going to give me y equal to 0. So 0, 0 is an equilibrium. And then y equal to -2 is going to give me x equal to 6 times 4 over 1 minus 2. So 24 over -1 is -24. It's kind of big. Okay, so those are my equilibria. And I don't really want to graph the null lines because I just don't. I suppose, right, we could graph them if we really need to. But what I do want to do is think about what's happening at these equilibria. So let's go ahead and find the Jacobian. So the Jacobian in general. So the way I always think about the Jacobian is it's the first function in the top row, the second function in the second row. The derivative with respect to the first variable in the first column, the derivative with respect to the second variable in the second column. So if we typically call this f of xy and this g of xy, that's the standard way of calling them. Then the Jacobian, the first row is the partials of f with respect to x and y. The second row is the partials of g with respect to x and y. The first column is the x partials. The second column is the y partials. Okay, so for this particular one, let's see, fx is going to be 1 plus y. Fy is going to be -12y plus x. Gx is going to be 8 plus 4y. And gy is going to be 0 plus All right. Okay, so now let's plug in our various equilibria. So if you plug in 0, 0, you're going to get, let's see, 1, 0. We're happy about that 0. 8, 0. Okay, so what are our eigenvalues? One of our eigenvalues is 0. Interesting. We had that happen on a test. I really don't imagine he would go there again. But yeah, I'm probably like, what happens? The eigenvalue is 0. What happens? It's weird. That's what happens. That feels. Sorry, I'm like, no, yeah, that seems good job, right? I love when I pick an example that is kind of funky. Yeah, that's right. Okay. Yeah. So our eigenvalues are 1 and 0. I have to imagine we probably have some sort of instability here. Because we have a positive eigenvalue. I feel like we should look at yeah, I think it might be worth looking at p-plane just to kind of take a look at that. Let that pop up while I. So yeah, I wonder when, sorry. I'm curious what the book has to say about this problem. 10.4. One second. They just asked us to find the linearization near equilibria, so it's not so wonky. Okay. And then the other one, -24, -2. So let's see, we're going to get 1 minus 2, so -1. We're going to get -12 times -2, which is 24, minus 24, which is 0. We're going to get 8 plus -8, which is also 0. And we're going to get 4 times -24, which is -96. So here our eigenvalues are -1 and -96. So here we definitely know we have a stable node, since both eigenvalues are negative. Let's go ahead and take a look, just so that we can, yeah, might as well see what this looks like, because I always think that's kind of helpful. So let me share my screen with you guys. Go ahead and type in these differential equations. So we've got x minus 6y squared plus xy. Got 8x plus 4xy. And -24 is our, let's make the x, okay. Let's go like -25. Whoops, not -25. I don't know. Let's see what that looks like. Oh, it looks funky. So over here at 0, 0, right, there's definitely some weirdness at 0, 0. It looks definitely kind of unstable to me, though. That's weird. And then over at our other equilibrium, -24, -2, so -24, -2, about here. Should be. I don't know about that. Right, it was definitely, yeah, x equals -24. Let me check. Yeah, that seems right. Okay. let's get a better look over there. So -24, -2. Okay, that's looking a little bit more. Yeah, it's weird though. It's definitely that zero eigenvalue makes everything super freaky. So yeah. Sorry for picking a bad example there. Sometimes that happens when you pick things out of the book. What else can we do with this? We can talk about the linearization. So this question did say, after finding your equilibrium, then find the linearization near each equilibrium. So how do you find the linearization near an equilibrium? Well, it really just comes down to a formula. That can erase this. So the linearization near 0, 0 is going to be L of xy is equal to, so here's the very general formula. It's f of xy plus, or x naught y naught, plus the partial with respect to x times x minus x naught, plus the partial with respect to y times y minus y naught. Yeah. And then yeah, sorry. That's the linearization of the first one. Yeah, sorry, I'm doing something slightly funky here. I'm going to try to do that right. And then, so that would be the linearization of f, then the linearization of g would be the same kind of thing. It would be g of x naught y naught plus gx times x minus x naught plus gy times y minus y naught. So at 0, 0, this is my fx, fy, gx, gy. So 0, 0, this is going to be, well, f of 0, 0 is 0, right? Whenever you're playing in equilibrium, this just becomes 0, because these were what the differential equations were equal to, right? So f is your first differential equation, and if you plug in equilibrium, the differential equation is equal to 0. Same thing for g. So then we're going to get fx, which is 1, times x minus 0 plus 0 times y minus 0. How not exciting. This one's going to be gx, which is 8, times times x minus 0 plus 0 times y minus 0. So these are kind of weird linearizations, right? This linearization here is just x. This linearization here is just 8x. How kind of strange. The other one, so for -24 comma -2, the linearization at that point would be, well, for f, it's going to be 0 plus the partial with respect to x, which is going to be 1 plus y, plugging in -2, so -1. I know I erased the other Jacobian I had, but it's -1 times x minus -24 plus partial with respect to y, which is going to be 0. So you get, 24 minus 24, y minus -2. And then the partial of the second thing, sorry, the linearization of the second thing will be partial with respect to x, partial of g with respect to x at -2 is going to give you 0 times x minus -24 plus 4 times -24 is -96 times y minus -2. So here, this one's equal to negative x plus 24, and this one's equal to negative 96 times y plus 2. Kind of strange linearizations, for sure. Let's see. Let's go ahead and look at one more example. Let's say we have a linear system of differential equations. So dx dt equals 3x minus 4y, dy dt equals x plus y. And we want to find, we really want to find the general solution, which means finding the eigenvalues and the eigenvectors. And let's say we have some initial conditions, which I'm going to make up and probably end up being terrible. Let's say we have x of 0 equals 3 and y of 0 equals 2. Probably not going to be great. So first and foremost, we want to find the eigenvalues. So here's our matrix, 3, negative 4, 1, 1. And let's find the eigenvalues using the trace determinant method. So the trace here is 3 plus 1 is 4. The determinant is 3 times 1 minus negative 4 times 1, which is 3 plus 4, which is 7. Okay, so then my eigenvalues are the trace plus or minus the square root of the trace squared minus 4 times 1 times 7 all over 2. That's going to be 4 plus or minus the square root of 16 minus 28 is negative 12 all over 2. That's not going to be nice. So we're going to end up getting, let's see, 4 over 2 is 2 plus or minus the square root of negative 12 is 2I root 3 over 2. So my eigenvalues are 2 plus or minus I root 3. Let's not find the eigenvectors, although we could. I would really be very surprised if he asked you to find some imaginary eigenvectors on your test. I know there was like 1 or 2 homework questions where you did have to find some imaginary eigenvectors, but usually not something we do in this class. So let's instead just talk about what this means for our solution of our steady state 0, 0. So having a positive 2 plus or minus I root 3 means we have, well, since it's imaginary, we know we have a spiral. Is it stable or unstable? Right. An unstable spiral. I suppose, let's go ahead and, yeah. So what we could do is, so an unstable spiral, a good question. Is it clockwise or counterclockwise? Counterclockwise. How do I know it's counterclockwise? Because I have a negative there. Because I have a note on my computer that says it's a negative there, it's counterclockwise. So if you're going to graph this thing, there is a point to this, I promise. There's something I actually think is worthwhile. So, right, we have an unstable spiral. And so what's happening, right, is we're kind of going like that, right? So we started at the point, x being 3 and y being 2. We know that we're going to kind of go right further and further and further and further out. So if I was going to try and draw the behavior of x and y versus time, right? So if I was going to draw, you know, like x versus time, I'd say, okay, well, I'm starting here. X is getting bigger for a bit, and then getting smaller, and then getting bigger. So x is going to start at 3, and then it's going to get bigger for a little bit, maybe up to like, I don't know, 4 or 5, and then it's gonna get smaller. But it's gonna like, right, the oscillations are gonna get larger and larger and larger because we have an unstable spiral, right? We're starting further and further and further from the origin. So the x values are getting bigger positively and negatively. And a similar thing would be true for y. Right? Y, we started at a value of 2, it would get smaller for a while, down to, I don't know, like -5, and then you get bigger up to like +7, right? And just keep getting smaller and bigger and smaller and bigger. More and more big, more and more small.